Okay, so we're back at it. We're going to work another sample problem from chapter 12 of your book. This is 1264 from the end of chapter questions. This problem deals with computing concentration units of measure. I did want to stress here at the onset that computing concentrations of solutes and solutions is really very fundamental to chemistry and very important. You should spend some time before the exam to review the definitions, make sure you know how to do that, because I do consider that pretty important, pretty crucial, okay? Everybody needs to know how to do that kind of thing. And of course the trick to this is there are many different concentration units of measure. We're going to review some of them here. You have to remember the definitions. You certainly want to be able to calculate them from information and convert between units as well, okay? So all those skills are things that we want to work towards. This problem demonstrates that, so I'm just going to work through it. In case you're struggling, you can kind of follow along and see what I'm doing, and hopefully that leads you on to success. So this particular problem reads, a solution is prepared by dissolving 20.2 milliliters of methanol. Now, methanol is a liquid organic solvent. It's got a molar mass of 32.04 grams per mole. We're going to dissolve that in 100 milliliters of water at 25 degrees Celsius. The final volume of the solution is going to be 118 milliliters. For methanol, this is its formula, this is its structure. Its density is 0.782 grams per mil. And for water, its density is right at 1 gram per milliliter. So the problem then goes on to ask us a series of questions. Compute the concentrations. It actually doesn't specify in the problem what you're supposed to compute the concentration of, which is a little bit confusing. I'm going to work with computing the concentrations of methanol in the mixture, because that is going to be our solute, and that's the more typical thing to do. A couple things to point out here at the start of this problem, I think are just kind of interesting and perhaps tutorial for you. Methanol is basically the simplest alcohol, as it turns out. It's got one carbon, hence the prefix meth, and the OL ending tells us that it's an alcohol. Its structure looks like this if you were to draw the Lewis dot. It's a one carbon molecule. And whenever you see this arrangement of atoms bonded to carbon, it's indicative of an alcohol functionality. That OH is indicative of an alcohol functionality. Of course, think about things that we talked about in class. This OH group is a pretty efficient hydrogen bonder, okay? Because you got hydrogen directly bonded to a highly electronegative element. So that's one thing to think about for this problem. Another thing I did want to point out as well, and this is just kind of interesting from, I guess, a chemistry perspective or physical chemistry perspective. Note in the problem that we used 100 milliliters of water, and that was carefully measured. We then used 20.2 milliliters of methanol. We mixed them together to make a solution. Notice that the final volume is not conserved. It's not 120.2. You might think that you can just add the volumes, but they were telling us in the problem here that the final volume, in fact, was 118. And that's actually pretty typical. There's no rule that says if you mix volumes, the final volume has to be sum of what you mixed. In fact, oftentimes it's not. That's because of the different intermolecular forces as the different liquids come together and mix. Okay, so I thought that was interesting to point out here too at the onset of this problem. The masses must be conserved, but volumes need not be. Okay, so don't think that volumes must be conserved. In fact, they're not. All right, so let's dive into this problem then to compute the molarity of the methanol in this mixture. Now, how are we going to do that? Well, I'm going to start by writing the definition of molarity. I'm a big believer in using figures and equations to help you along your way. Because if you can draw out a picture of what you're dealing with, or you can write an equation, it really helps to organize your thoughts. So if you're struggling with this, don't be afraid to write out the equation on a piece of paper. There's nothing wrong with doing that. In fact, I oftentimes do it myself a lot to organize my thoughts, because that's half the battle sometimes. So in this particular problem, we need to find molarity. So we need to know the number of moles of the solid, which is of course our methanol. We need to know the liters of solution. After I write my equation, I usually look for something that's easy to find, just because it gives me some momentum in this problem. as I look at this denominator, I'm pretty excited because in my problem, I was told that the final volume was 118 milliliters, which is, of course, equal to 0.118 liters. Now notice I did the conversion in my head here. Hopefully you're good enough to do that. I just divided by 1,000 because, of course, there's 1,000 milliliters in 1 liter. But 118 milliliters is 0.118 liters. Okay, so I just put that number there. That's a freebie from the problem itself. Now the other thing I need to figure out is the moles of my solid. That's my moles of methanol. I don't have that yet, so I'm going to need to compute it. Again, I write out my formula. If I could find how many grams of methanol I've got, I could divide that by my molar mass in grams per mole. I'm in business. I know how many moles of methanol is present. Now, let's see what I know about my methanol from the problem. Well, I was told that I've got a volume of methanol, 20.2 milliliters of methanol. If I read through the problem more, I was told that the density of the methanol is 0.782 grams per milliliter. So it seems like I can use that density as a conversion factor. Grams per milliliter. My milliliters cancel if I do multiplication. If I bring that number down, I do 20.2 times 0.782. It looks like I've got 15.7964 grams of methanol. Okay. If I'm paying attention to sig figs here, I should probably truncate this to 3. I'll do that at the end of the calculation because we're going to go to moles here in a second. Okay, so this is grams methanol, but if I'm going to compute molarity, I need to know the moles of my methanol. So how many moles of methanol do I have? Got to do a little bit more work, okay? But this is not too terribly difficult. I've actually already started over here, right? I plug in how many grams I've got. I'm going to divide by my molar mass. That was given to me in the problem here as 32.04 grams per mole. Okay. Grams unit cancel, and I'm left with 1 over moles, which is just going to be mole units. And if I do the math on that, I get 0.4930 moles of my methanol, my solid. Okay. And again, if I'm going to truncate that to sig figs, I had 3 here, so my answer should have 3. I'll just ditch this 0 and write 0.493. But you can see what I've done. I computed the number of moles of methanol, and now I'm ready to compute molarity by taking my number of moles divided by my liters of solution. So I've got one more step. I just need to do that division. If I do that, it turns out the solution is 4.17 moles per liter, or 4.17 molar, as a chemist would say. If I want to think back to sig figs, I had 3 and 3, so reporting 3 is just fine in this particular case, all right? All right, so that's my molarity calculation. That's the first one of the bunch. There's actually several that we have to compute, okay? Let's go through this and try our hand at the next one. Hopefully you've written that down so you can follow along, because some of the numbers that I'm going to use will come back up again, okay? Part B of this problem is to compute the molality of the methanol. Okay. So the next question is well, what does molality correspond to? You have to know the definition if you're going to get this right on the test or on the homework, right? So start off by writing your definition. Molality, remember, is the number of moles of the solute divided by the number of kilograms solvent. The mass of the solvent has to be expressed in kilogram units. That's very important. Got to remember that, okay? So, where do we find these numbers? Well, in part 1 to this problem, we solve for the number of moles of methanol. I already showed you that computation, so I'm not going to go back through it just in the interest of time. But remember, we found there was 0.493 moles of methanol, okay, based on the conditions of this experiment. Now we need to figure out how many kilograms of solvent we've got. Well, first we need to decide what the solvent is. Remember, the solvent's always present in highest quantity or determines the phase. So the solvent in this particular case is our water. It's present in largest quantity. All right, so we've got 100 milliliters of water. Now, we don't need milliliters or liters here. We need kilograms of the solvent. Fortunately, we're told that the density of the water is 1 gram for every milliliter. So if I've got 100 milliliters of water, I also know I've got 100 grams of water. So this is actually really, really straightforward. Because I know I've got 100 grams of water by virtue of the density, I know I've got 0.1 kilograms. So I've got the number of moles of my solute, which is my methanol, present in lower quantity, divided by 0.1 kilograms. It's like multiplying by 10, basically. So I would say this solution is 4.93 molal in methanol. Molal being M-O-L-A-L, molal. Okay, that's the molality. This unit of concentration usually comes up when we're talking about colligative properties, and that's why it's important. We'll see that later in chapter 12. Okay, so you got to remember the definition if you're going to compute the molality. Nonetheless, we've succeeded. Let's move on to part C of this problem. Part C, we are tasked with computing the percent by mass. In my experience, that's usually abbreviated as percent M/M. It means percent by mass. It's kind of lingo that chemists might use. So again, we need to think about our definition. Percent by mass is pretty easy to understand. It's just the mass of the solute of interest divided by the total mass of the solution multiplied by 100 to express as a percent. Okay? We need to find those numbers. If we do, we are in business. Okay? Now, previously in this problem, when we were computing the molarity, we were forced to compute the mass of methanol. So if you forgot that, page back, we used the density, where is it there? The density and the volume to figure out the mass of the solute methanol. We decided that there was 15.7964 grams of methanol in this solution by virtue of the details, okay? So all I need to do is take that number and divide it by the total mass of the solution. Now, we didn't really figure out what the total mass of the solution was yet. In part B, when we were computing molality, we decided there was 100 grams of water present. And that was easy to figure out because we knew we had 100 milliliters and the density was exactly equal to 1. Okay, so we could compute the 100 grams. So that's very helpful because that's one component to our mixture. And the only other thing that's present that we were told is our methanol, which we know has a mass of 15.7964 grams. Okay. So by using the definition and the knowledge of the system, we can plug in numbers. We know the mass of the solid's this, and we know the total mass has to be this plus this, or the sum of those two numbers. We multiply by 100 and express as a percent. If we do the math on that, that works out to 13.64% by mass. Easy enough. The next computation for part D asks us to compute mole fraction. Mole fraction of the methanol. So again, we need to start with an equation so that we can fill in the variables as needed. Okay. If you think about the definition for mole fraction, it's essentially equivalent to the moles of the solute. In this case, that's the methanol, divided by the total number of moles of all components. All components, okay? Now again, referring back to some previous numbers to save some time. Moles of solute, that's simply the moles of methanol. We computed that in part A for this problem. If you're struggling to figure out where that came from, review back to part A where we were working on that, okay? But remember, we had 20.2 milliliters. We used the density to find grams. We took grams, we divided by the molar mass to give us the moles of the solute. And we found that we had 0.493 mole of the methanol. Okay, so that's the moles of the solid. That number also goes in the denominator of the fraction because it makes up part of our mixture. But there's a second part of our mixture as well. There's water. To finish this problem, we need to know how many moles of water were present in our mixture. Now, how are we going to figure that out? Well, previously we decided that we had 100 milliliters of water, and the density of the water is 1 gram per milliliter. This essentially means that I've got 100 grams of water in my mixture. Of course, if I use my conversion factor to convert to moles by dividing by 18.02, which is the molar mass of water, I can compute exactly how many moles of water are present in this mixture. And if I punch the numbers in my calculator, I get 5.5493 moles. That's my response for number of moles of water. I take that number and I place it down here in the denominator of my fraction. 5.5493. Now, the bottom of the fraction describes the total moles of all components present in my mixture. So I have the moles of my solute divided by the total moles. And that's equal to my mole fraction of methanol. If I do the math on that, it works out to 0.08159. That's the number that I get off the calculator. If I want to pay some attention back to sig figs, you have to think a little bit, well, where did this come from? I'm going to, again, assume that there's a decimal point here, so this gives us 3 sig figs. This is also 3. Our density is reflected in 3 sig figs as well, so our answer probably should have 3. So I might round this up to 816 at that point, okay? And that's my mole fraction of methanol. Okay? Simple enough. We use mole fraction for Raoult's law, and that's why we need to be able to calculate this. Because if you're going to use Raoult's law for vapor pressure lowering, which is one of our colligative properties, you need to know mole fraction. We have one more part to this problem now. Part E. This one's going to be really easy. Probably the easiest one because it's mole percent. Mole percent. What is our mole percent of methanol in our mixture? Well, mole percent is simply the mole fraction times 100 to express the number as a percent. Remember, mole fraction is between 0 and 1. Mole percent is between 0 and 100%. So this one's pretty easy because in that last step we computed the mole fraction of our methanol and it was equal to 0.0816. All I need to do to compute my mole percent is multiply that by 100, which of course is like moving the decimal place 2 spots. That yields a result of 8.16% on a mole basis. This concludes this example problem.